Okay, once again, ladies and gentlemen, dear student, welcome to this second session of our numerical method class, numerical method 2 class, which is a continuation of numerical method 1. Even though they are not that, yeah, they are related somehow. It's a continuation. I promise that today I will upload the first tutorial. It's ready. Let me quickly even do that. Let me quickly do that. In the meantime, I will say something about what we did yesterday. So yesterday, I recall what is the least square method, because least square method is a concept that we already encountered in MMO. So that's why I think we don't really have to spend that much time. The only thing I can do is to recall some concepts. And assignment, I wanted to say this tutorial 1. In tutorial 1, the first part is on least square method. So that's why I thought it would be the opportune time for you to start solving the problem. Instead of waiting after 1 week, 2 weeks before I release tutorial 1, it's good for you to start now from the very first day. Okay, let's say from the second day, because today is the second day. The day of the second lecture. So if you start there, at least you'll be motivated, you'll be boosted instead of waiting, because when you delay, people who are hot will cool down. So that's what I want to hit the iron when it's still hot. Right. Okay, that being said, least square method, what is it all about? It's part of the approximation theory. You have a set of data points that represent a certain quantity. It might be the weight of people in the individual in the population. It can be the height of individual. It can be anything that you want to measure. No, now you sample the population, and then you have a certain information, and you want to use that information to make decision, maybe to project what will happen, or to project something about the entire population, something like that. That for that purpose, you need to approximate that function, or you want to get a certain representation of the function or the quantity in question. So for that, you need to approximate that function. It doesn't mean that it's exact, but you need to approximate. And the approximation should be realistic in such a way that if you want to interpolate, or you want to predict, you want to find extra information, it will give you something that is closer to reality. So that is about approximation theory. Now, among the methods, you have a polynomial interpolation that we tackled during the first semester. And I explained the drawback of the interpolating polynomial. I say that interpolating polynomials are not that good when it comes to representing a function or approximating a function directly. It can be used in other contexts, like in numerical integration, differentiations, things like that. You can use that function to approximate and then differentiate or integrate, as we will be seeing later on when we tackle numerical integration. But if you want to find the value of a function at a given point, interpolating polynomial is not the best option, because of what I already told you, the wrong phenomenon, or due to the fact that if you have many points and you will be approximating with a single polynomial, and if you have a polynomial of a higher degree, that there will be wiggles or oscillations. That's the behavior of polynomial of high degree. You will oscillate. And because of oscillation, the error will be very large. That's why it's not good to approximate function. So the approach of least square is better, because with the least square, you reduce that error. Because remember that the purpose of the least square, you have the set of data points and then the approximant. Yeah? You reduce that error using the second, you use the L2 or the two norms. That's the least square method. You minimize the two norms of the error. So you make sure that that error is minimized. If the error is minimized, it means that your approximation will be realistic, right? Well, so that is So when you compute the two norm of the least square, the two norm square of the error, you obtain a function of the parameter, because remember the function you want to approximate has one or many parameters. So in order to find those parameters, you solve the Normal's equation, and for the Normal equation, what you do, you impose the optimality condition, meaning that there will be a turning point if and only if the partial derivative, right, with respect to quantity, are zero. That's the first derivative, let's say you test or something. Yeah, first derivative test, something like that. You first find the critical point, which is that one. And so that will give you the Normal equation. And once you solve the Normal equation, you obtain the coefficients. Because the Normal equation will give you a system of linear equation in the number of unknown. You solve that, and then you get the parameter, substitute back in the equation. It gives you your least square approximation. Right. So least square you can approximate using a line, which is common. You can use a quadratic polynomial or a polynomial of degree n. But that polynomial of degree n is completely different from the from polynomial interpolation, the way we addressed during the first semester. Completely different. Because here you are minimizing, the error will be really minimum. And the degree of the polynomial has nothing to do with the number of data points. Whereas in polynomial interpolation, there is a direct correlation between the degree of the polynomial and the number of data points. Because remember, if you have a large set of data points, the degree of your polynomial will also be very large. Whereas when you use least square method, you can have, let's say, thousands or even millions of data points, and you decide to approximate with this cubic polynomial. Because if you recall what I told you, with cubic, if you remember spline, cubic spline, the way I explained yesterday, and you saw even with a schematic, when you have a cubic spline, the cubic spline can easily change direction. If you want to approximate a function, for instance, that has a turning point, or no, an inflection point, a third degree polynomial will easily adapt and adjust to represent an inflection point. What the second degree polynomial cannot do. Right? Now, if you have a turning point, a straight line will not do it. So with a cubic spline, it can easily adjust and find the correct direction. So if you are asked among the polynomial, which one will give you a better approximation, I will tell you the best choice will always be a cubic spline or a third degree polynomial, because it has a curvature and it can also approximate an inflection point. Right. Okay. Now let me upload the tutorial. And after that, we'll go straight to our MATLAB code, because that's what I promised yesterday. I hope you haven't forgotten that I promised for those who are late or who were even absent. Erin Fried was not there. So I don't think she was there yesterday. Katua, were you there yesterday? No, we're not there.
I was there for half of the class, then my data got
So you are fine, half of the money. Half of the money is $50, so you are fine, half of the money.
Okay.
Class representative, write down her name. She will give you half of $50, which is $25. But last semester, you didn't even tell me how much you got. But class representative, if you don't do that this semester, you pay for the cake. Nanona, are you with us? Hey, I hope the picture is not present, but the body.
Yes, sir, I am.
Oh,
I
okay.
am here.
All right. So don't forget, because if at the end of the semester I ask you, how much do you have in the account, in the class account? If you say nothing, then you'll buy the cake.
Okay, sir.
Okay. So when I find somebody, just write down the name. Because normally we're supposed to celebrate. And all of you who passed the module were supposed to celebrate and buy a cake and rejoice and enjoy the cake. All right, so I will upload the tutorial 1. We have to be up to date. There should be no delay in what we are going to do. You see that most of you, if you start solving those problems, you will all pass. And I will be happy. I will be happy if you all pass. And be careful. This semester will not be like the first one, because that's why I'm encouraging you to start working. Even before we tackle some of the topic, if you can be proactive, read in advance. I encourage you to do that. Because the second semester is not like the first semester. In general, people fail more during the second semester because of the complexity, or because of the new concept. So if you sleep or you slumber a bit, you'll be surprised. And I don't want that to happen. That's why I want you to be alert and start addressing critical problems. Okay, so I gave you this yesterday as a homework. Have you done that? Our student who attended half of the class, have you done half of the problem? Or you did all the problem? The two or
Not yet, sir.
why? Even half? Since you
I was
like,
trying to access the class at 12, but I couldn't get through, so I can write down the homework, sir.
but you were supposed to download. You were supposed to download the. You were supposed to download the lesson.
Yes, sir. I was trying to do that at 12. It was not going through.
What do you mean? What do you mean? What do you mean?
I was trying to watch the video itself also, sir, for the class.
You are trying to justify yourself.
No, sir.
Yeah, you're arguing. You cannot acknowledge that you failed to do what you're supposed to do. Now you want to complain. Now what are you accusing? You're accusing the internet.
No, sir.
Now what should I do? Should I ask internet? Should I punish internet? How will I punish
No,
internet?
sir.
I cannot punish internet. But at least I have you at hand. Do you want me to fine you another $20, $25 so that it makes 50?
Okay, sir.
Now you say, okay. I'm asking you the question, do you want me to? Okay, so if you have a lot of money, it's fine. Then you pay 50 in total.
Okay, sir.
Oh, apparently you have money, eh? Can you even put 100 so that there will be enough money in the class account? How much can you put? I can see that you have money. Any bonus? Or do you want to add extra money? Maybe 50 is small for you.
No, sir. 50 is enough.
Oh, it's enough. Okay, great. So, class rep, you heard what she said. She's willing to put money in the account. Okay, so now, where am I? Okay, where is that? Okay, tutorial. Okay, I'm busy uploading. I'm busy uploading the tutorial. Some of you might be asking, what is it doing? I'm doing something. Okay, so I am about to upload on the platform. I want you to. Okay, so I'm here. Okay, so let me see. What is this? Okay, attach. Upload from my computer. Yes. Yes, 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 yes. 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 Not. Yes. Tutorial 1. Great. Yes. Yes. Oh, yes, yes. Come. Upload. Great. Okay. So, okay, I still need to press to, okay, to upload. Hi, dear students. Please find attach below one. That. Great. Now, let me upload it. Hi, dear student, please find attach below tutorial 1. Regards. Send. Okay, please can you check? Can you check on the e-learning platform if you can see the tutorial? Can you see it? Is it there? Can you see? I can see it. I want to confirm that you have access to the file. I just sent it. 8:51.
Sir,
Yes.
We can, sir.
it is there. We'll just confirm if we can download it. But
Sorry?
we can see it is there.
Yeah, you can download it.
Yeah.
That's why I uploaded. If I upload something, it means that you can download.
Yeah, sir, I'm saying we'll confirm if we can download it because we can see it. So, yeah, it is. We can download it. We have access to it.
Okay, great. I'm happy because at least we are going somewhere. You already have first tutorial, so start solving those problems. It is time now to start doing all the problems related to least square, because test 1, similar problem will come, right? During test, the first test. So make sure that you get the full mark. Really, related to that part. Good. We are going somewhere. Okay, now let's go to our MATLAB session. So this is what I said you will be doing today. So if you look at the, let me look at 9, 8, it's this one. You see this problem, this set of data point. Let me even write it somewhere so that I will not have to come back. Unfortunately, some of you are using the cell phone, so you don't have Python. What I'm going to do now with MATLAB, you can do the same with Python. Please try that with Python, because remember I told you you have to. In fact, it's a must for you to know a programming language and know it well. And the easiest and one of the most popular programming languages nowadays is Python. In all the institutions, in research now, everybody's going towards Python. So please bear that in mind and make sure you know that language. Was it during the first semester? I think was it during the first semester? I think I emailed, did I email or uploaded? My Python classes. I think I gave you, I emailed that to you, huh? Am I right? During the first semester, I think I sent you my Python classes, my notes. Have you forgotten? Or I haven't done that? During the first semester, in the beginning. Hey guys, are we together? Huh. I hope I'm not dealing with ghosts too.
No, sir.
How come? How come? Class representative, tell me.
Yes, sir.
I sent, right?
I don't recall, sir, sending it.
How come you don't recall? In the beginning, you want to say that I did not stress on Python?
No, sir, did stress on Python. We also
Good.
did a few.
And your first assignment, was it not on Python? Your first assignment, what was it about?
I don't think it was on Python, sir.
What was
But
it?
sir,
So
in class, sir, did stress on Python, and we did a few examples.
And I
Python.
couldn't have done it without uploading or sending my Python notes to you. I usually do that.
Sir's Python book.
Not a book, a note. My notes. It's like a book.
Okay.
Yeah,
It's basically a book. Yeah, that's what sir sent us. Yeah.
So why were you saying that I didn't send you?
Oh no, sir said emailed us videos. I think that's where I was like, no.
No, I'm talking about the booklet. I sent you a booklet. I remember.
Okay, no, the booklet, yes, you did.
My
apologies.
Now, my question now is that, did you go through to make sure that you learn Python? You see, that's my problem with you. That is my problem. Anyway, I will not start another trial today. So let me forget about that one. But make sure that you learn Python. That's the most I can see. Or the least. Okay, that's the least. Okay, so I will write the set of data points on a piece of paper so that when I will move to that section, I will not have to come back here. So 3 is 2.27, 4 is 6.50, 5 is 8.98, and finally 6 is 9.88. So we are going to, you see that when you apply the least square method to this, if you want to use a second order polynomial, right? This is our normal equation. This is the normal equation that we are going to solve, but with the degree of our polynomial being 2 here. So in this expression, our n will be 2. If you take second degree polynomial, Pn, n is equal to 2. So if you come here, we take n equal to 2. And what is the value of m? M is the number of data points. You can see here, right? To approximate a given set of data, here, xi, y sub I runs from 1 to m. So m is the number of points. You have m point, n is the degree of the polynomial. So if you come into this normal equation and substitute those values, you obtain this. You can even see it's written here. For this problem, n is equal to 2 and m is 6. So if you look at the table, you can see 1, 2, 3, 4, 5, 6. So we have 6 points. Now we substitute that in our normal equation and we get this. So this is a system, how many unknowns? 1, 2, 3 unknowns. 1, 2, 3, and how many equations? 1, 2, 3. So we solve a linear system that is consistent, and we are sure the solution will be unique. So now we sum all these terms. You can see all these terms or these coefficients. You can sum them, right? You can sum these terms, and that's what we are doing in this table, right? So we write the individual component for each I, and then we sum at the end. We sum all of them here, and it will give us this coefficient, and we obtain our linear system, which is given by this. So this is our final linear system. So we can solve this using what? We can use MATLAB to do that directly. You can use MATLAB, you can use Python, any programming language, right? Okay, from MATLAB, you can see that we need the data. We have the X component, Y component of the data in the table here. You can see that for X, we have 1, 2, 3, 4, 5, 6. And for Y, we have all these entries. And that's why we build here in this matrix here. Yeah. Right. Okay, we put the dash here. Dash here represent the transpose, right? In MATLAB, dash or the apostrophe that you see here represent the transpose. Okay, so now what we will do from here, we'll move straight to MATLAB, right? I will share the MATLAB screen with you. And you will see exactly what each of these command is doing. Okay, so we will run this. So let me share the MATLAB screen. Let me share the MATLAB screen with you guys. MATLAB. Boom. It's not witchcraft, guys. So you can see that's MATLAB screen. So don't go to the village and say, hey, oh, I saw terrible things there on the screen. No, it's not witchcraft. This is science. This is IT. It's technology. Good. So this is our screen. So if you recall what was done, there was clear. Okay, let me do something for you. Let's say I type stuff here, I enter, you whatever there, whatsoever, I enter, I assume that there are many, many, many things there. Boom. Okay, good. Now, if you recall on the previous slide, you saw this one, clear. Do you recall that? Do you recall having seen this? Clear, that one. That's what I want to show you. Hey, guys, are we together?
Yes, sir, we saw.
Good. You're the only ones answering me. The other people, they don't care. Eh? It's as if the parents chase them. Oh, go to school. Oh, okay. Since you push me, I will go there. I will not say anything. At least the lecturer will know that I was present. If he has anything, I will not say anything. If he wants to punish me, I don't care. Anyway, I hope you are not the type of student who is forced to come to school. Anyway, you are not even forced to be there. Oh. Okay, so now if I press enter, what do you think will happen? Okay, let me press enter. Now, you remember what was here? Do you see the cursor?
Yes, sir.
Okay, let me repeat. Let me repeat. I will clear. I will do this. Okay, I will start afresh. I will start afresh and tap what was there before. And you will see what I'm going to do. It's not witchcraft. It is IT. So what was there before is that. It's not witchcraft. You see, everything reappeared the way it was before. It's not witchcraft. You see, okay. It's not witchcraft. Don't say, hey, he did something I did not understand. No, I tried to reproduce what was there before and it's there. It's not witchcraft. Now, do you see this portion of the screen? You call it a workspace. This one, the workspace. Do you see it? What do you see inside the workspace here? You can see that you have a cell here, and the name of the cell is ans for answer, and you have these values 4.1. This you can see. Can you see it?
Yes, sir, we can see.
Good. Good. Now, when I will press clear, you will see that something will happen to these cells. I mean, to these ants. So here, if I press enter, what happened? Can you tell me what you realize? What happened here?
It cleared everything that was there, sir.
Good. So everything, and what you see here is what is in the memory. Particularly for this particular session, whatever is here is the workspace. That's what is in the memory. Let's understand it that way. So if I say clear, it will clear everything that is there. Right. Why do we need that? Because we want to avoid conflicts. Something that you clear to release the memory and to have enough space in the memory to do whatever you'll be doing. So that's for clear. Now, if I want to clear this part, this command window, I want to clear what is above, I will say CLC. Now, this one is to clear the screen, because this is our screen. If I want to clear that screen, I will say CLC, right? Enter, you see? You see now. Great. So that was the purpose of the first command, clear, to clear whatever is in the memory here. So we proceed. Now we enter the set of data point. So we have the X component is from 1 to 6. I can enter 1, 2, 3, 4, 5, 6, right? Close, put the apostrophe here like that, right? And semicolon. What is the purpose of the semicolon in MATLAB? Is to prevent the program to display the values of X. Now, if I enter, you see that X is not displayed on the screen here. But if you come back to the workspace, you can see that X is there. Do you see X in the workspace here? Do you see the cursor?
Yes, sir.
Yes, sir.
Great. So that is our X. You see, we enter X here, and it appears directly in our workspace. It's there. Now, if I want to display X, I will do that. I will just type X, enter, and it will display X here in the screen. So that's the purpose of the semicolon, to prevent X to be displayed on the screen. Now, you can see that the apostrophe have transformed this row vector, this column vector into a row vector. You can see that our X now is a column vector, column. This is column, right? This is a column vector. When we write this way, it's a row vector. Okay, let me show it again. If I remove, let me call this XR to say row. If I remove the apostrophe, like that, let me also remove the semicolon. Now, if I press, you will see that it will display XR in a different, you can see that this is row, and this is column. X is a column vector, but XR is a row vector. So if I have a row vector I want to transform into column, I put the apostrophe. That's the purpose of that apostrophe, to convert row into column. And that's why sometimes when I write a vector in a row form, I put the T to transpose it. This is an explanation of that. Is that clear? Oh. Now I will say clear XR because we don't need that XR. Good. You see that X has disappeared from the workspace. It's no witchcraft to open your eyes and see. Okay, so we have our X, which is a column vector. As I explained already, this one. Let me enter again. This is our X. The column vector is here in the workspace. I do the same thing for our Y. So Y will also be a column vector. So what are the components? I have 3.54, comma, 4.55, comma, 2.25, comma, 6.50, comma, 8.98, comma, 9.88. I close and apostrophe to transform it into a column vector. Enter. So I have my X and I have my Y. So what I'm going to do now, I'm going to plot the clouds, right? Represented by the set of data points. So I have X, comma, Y. So I plot Y against X. So the variable the independent variable comes before the dependent variable. So Y depends on X. So I first put X and then Y. Exactly the way you write the coordinates of a point, X, Y. So we put X, Y there, and then comma. Now I want to represent this using O, or small circle, right? So that's what I do. Then I can close the arguments of the function plot. If I enter, I will see the plot, right? Okay. Can you see the figure? Or I am the only one to see it?
I can't see it, sir.
Do you see or you can't see?
I can't.
Oh.
So we can't see
it because you didn't share it with us.
Yeah. But you see that with Python, unfortunately with MATLAB, okay, unfortunately with MATLAB you cannot see. Maybe I should have used Python, because with Python I can embed the graph inside the browser. If I use how do you call that? Jupyter Notebook. With Jupyter Notebook, I can embed any graph within the browser, so in such a way that you will see it on the screen. But here, MATLAB, you don't even see. I am the only one to see the figure, but I cannot embed it here in the command windows. That's the drawback. So you see already the power of Python. That's another advantage of Python. What should I do now? Because everything that we are going to do now, you will not be able to see it. So what I would do, unfortunately. Okay, but anyway, try to do that. Try to do that with MATLAB on your own. And I think for next time, I will prepare something to do this, something similar on in Python. We don't have enough time now. We are left with about 17 minutes. So that if I want to go there, I will have to load and all that. It will take time. So let us just leave it for now. Let's leave it for now. But I encourage you, you can reproduce this in Python. Try to do that. Try to learn. If you don't get it, you can Google, you go you look for help. But please make sure that you can reproduce what we are doing in Python. Are we together? Are we together? Okay, so now if you go to your notes on page 7, you will see the graph that I obtained when I press enter. It's the same. Please go to page 7 of the notes. Since you all have the note, you downloaded the note. If you go there, you will see. That's exactly what I obtained when I press enter. Okay, now we will proceed. We are going to approximate that using our second order polynomial. Right. Now, for the second order polynomial, our normal equation is a system of 3 equations in 3 unknowns. Wait, how many? 1, 2, 3. That is for the normal equation. Let me quickly go and look at that again. M is equal to 6 here. Wait. 1, 2, 3. M is equal to 6. M is equal to 6. I don't know what is happening here. So what is all this? All right. Okay, so let's proceed. Let's proceed with the notes. Please go to page 7 of the notes. Are you there? Okay. Now, if you okay, I think I will have to toggle between the two. I have to toggle between the two. Otherwise, it might be a bit difficult. That's another drawback. Here. What's happening? Okay. Okay, I will toggle. I will toggle between the two. Instead of asking you to go to that, I think I can share that again. It's not that convenient to go, come back, change, but let me try. Let me try that. Okay. Okay, so this is where I am. So I was saying that when I press enter, this is the figure that I obtained, this one. We have our 6.1, 2, 3, 4, 5, 6. Okay, and now this is what we want to approximate. We want to fit this directly from the data point. Right. Now, if we take this and apply to each point, that is, in my equation, I substitute this value of x1. I substitute x1. I write p x1 is equal to y1, p x2 equal to y2, p x3 equal to, and so forth up to the last one. It will give us a system of 1, 2, 6 equation in the 3 unknowns, this one. And these 3 unknowns. So if we do that, this is what we obtain. So for x1, we substitute x equal to x1 here. X1 is 1. And then y is 5.54. We do the same thing, x equal to 2, substitute the corresponding value, x equal to 3, 4, 5, 6, and then we get this. Right. Now, this one, for this particular one, we can see that we can use a least square because here the system is overdetermined, right? Now, the least square here, for the least square, we just solve this directly from MATLAB using the least square method, but there are many approaches. We can do something similar. So you can see that this linear system If we write it in this form, C is for the coefficient, and A is our unknown. So A, the coefficient are A's, right? You have A0, A1, A2. So that's for our A. And B is this right-hand side. This right-hand side, 5.54 up to 9.88. That's what you have into the B. So now what we are going to do, we are going to apply the least square method to see what the result will be, right? So if you apply the least square method, we need to construct our matrix C. We need also to construct A and B, and then solve. You will see that the backslash, the MATLAB backslash, will perform the least square without you telling MATLAB that please perform the least square method for me. Do you understand? Because this is what we are doing it directly. We are using the table directly. So what we are doing here, we are using this directly. That is, we construct this, we construct X, we construct Y, and we use the least square directly. And then we compare the result with the cloud that we plotted here. So that was the first step. We plotted the cloud of point, which is this one. And then we use our X and Y vectors, these two, X and Y, the table, we use the table, and then we ask MATLAB to perform the least square method, and we plot all the results together. So now, our C, if you look here, the coefficient here, the C, it will be the coefficient, this one. So for the coefficient, you can see what we are going to do. We will enter the first one, which is everything is 1, and then we will take X and X squared. So now for this one, this coefficient, you can see that we have, in terms of our coefficient, you can see that the first column here is 1. You can see that the coefficient of A0 are all 1. You see, the coefficient here, you have 1, 1, 1, 1, 1, 1. And the coefficient of A2 are 1, 2, 3, 4, 5, 6. And the coefficient of A2 are 1 square, 2 square, 3 square, 4 square, 5 square, 6 square. And that's exactly what we are doing here. So for the first column, everything is 1. That's why you have 1 here. Now the second column of C, you have 1, 2, 3, 4, 5, 6. And 1, 2, 3, 5, 6 represent what? It represents the X values. This one. 1, 2, 3, 4, 5, 6. So these are the entries of X. So that's why you have X here. This one. X. And now, the third column, you can see that is X squared. The component of X squared. That's what we have here, the third component of the matrix C. So that's why we squared them here. Now you can see that the difference here is that there's a dot here before the square. Is to say that it's not a matrix multiplication. We are not multiplying X by X, but we take each entry of X and we square it. That's why you have the dot here. We call it element-wise. So when you see the dot there, it means that what we perform, the square that we are performing to X, we are doing it to each of its entries. You are not multiplying X by X. If I don't put the dot, I'll be multiplying X by itself, which is completely different. So the dot is an element-wise operation. I hope it's clear for everybody. So that's what this is all about. So if we perform these three, we will have constructed our C component, I mean the C matrix. And for B, if you look at B here is what? Is this one. And what is this? This is Y. 5.54 up to 9.88. If you look at the table, you can see 3.54 up to 9.88. You can see that these are the component of y. And it's exactly what we enter here. So that is it. So B is y. Now we are solving for what? For A. A is our unknown. We are looking for this coefficient, the A's, A0, A1, and A2. So that's what we are solving for. So you can see that if you use backslash, okay, what you have been used to, you know that backslash is to perform what? Gauss elimination. Gauss elimination that we encountered during the first semester. Backslash in general will perform Gauss elimination if you have a square matrix. But here our matrix is not square. Our matrix is not square. You can see we have 3 rows but 6 columns. So C is not a square matrix. So when the matrix is not square, when you have a rectangular matrix and you use backslash, MATLAB understands that it needs to perform a least square operation or the least square method. So backslash in MATLAB might mean Gauss elimination or least square, depending on the size of the matrix. If the matrix is not a square matrix, it will perform the least square method. If it is square, it performs Gauss elimination. Or any other method depending on the property of this. This is a powerful command, the backslash. It doesn't only perform Gauss elimination, it can also perform Cholesky if the matrix here is a symmetric matrix. So it's really an advanced command. Okay, but please, since this lecture is being recorded, you can go and listen again to understand that the backslash is not just Gauss elimination. It does a lot of things. It's a very powerful method. So now, when we solve that, we can extract the components A0 from the first component of capital A, and then A1 from the second component, A2 from the last component. And now from there, we can obtain the equation of this equation, the fit, this one, this equation. You see that this is the equation that we will fit. We want to fit the data using this quadratic equation. So we need our A0, A1, A2, and write our formula. So that's what we are doing here. Once you have our A1, A0, A0, A1, A2, we use this. And then we can plot. Okay, the plot is not here. I think it should be somewhere below. It's this one. So this is the plot. When we perform that, we obtain. You can see that this is a quadratic. So this is our 6 point. 1, 2, 3, 4, 5, 6. And now when we fit, you can see we have our parabolic equation. I think it passes only through the first point, but the rest is not. But this error is minimized. You see that this error, this is the error. This one. It's been minimized compared to polynomial interpolation. Because if you use polynomial interpolation, you see we go through all the points, but the error will be very large. Right. So this is what you are supposed to get if you follow this entire procedure. This one. So unfortunately, that graph went and appeared farther. It's not on the next page, unfortunately. So give the result. So that result is on page this one. This is page 10, unfortunately. It's on page 10. It's this one. Right. Of course, which is similar to what you have here. Is it really that? Yeah, because it's the same. almost the same. It's the same data point. You can see. Is it really the same? Anyway, it's something similar. All right, so do you have a class after this one? Because it's already 29. I think in terms of explanation, I already explained everything. The only thing left now is just to go and enter this command, which you can all do. You can all perform this. Do you have a class after this? Class rep, Nanuna?
Yes.
Okay.
Yes, sir.
I think I will release you. Thank you for your kind attention. We'll stop here for today. Please go and do this. Next time, I think I will prepare a similar practical for Python. We'll do that on Python for next time. But you can also prepare. Start doing that. Thank you. God bless you and see you on Friday. Bye-bye.